Thanks a lot, and thank you all. It's my great pleasure and honor to talk about the subject I have loved for nearly 30 years. But I got a bit stressed how to talk about it in 10 minutes or 8 minutes. So I thought about it. I think I'll try to answer two basic questions first. Do we need wireless power? How is wireless power transfer achieved? Then talk a bit about applications. I think that part is a bit easy to understand, and also relate that to research work, research contribution by our research group from the University of Auckland. They discuss a bit about the challenges and the development trends of wireless power supplies. Do we need wireless power? We know we all need power. That's a driving force. Without power, nothing would work. Musk said, okay, the end of AI, it's power. Who holds the watch, who will take control, right? But do we need wireless power? That's a question. So here, there's a picture I got from YouTube. Okay, if we have an electric stove, which is more environmental friendly, but it needs a lot of wire to connect up. It's a very innovative, right? Innovative to have a slipper, okay, to connect them up. Okay, it works, but you can see the reason, right? We can see the problem, okay? So we can see in such a case, there's clear need for wireless or contactless power transfer, right? That's just one situation, but more systematically, so the motivation behind wireless power transfer I can summarize into this list. So basically, it's more convenient for mobile devices, like mobile phones. But the current solution is battery, right? So battery, if you connect up, it's a problem. So new battery manufacturers, they try to get rid of the connectors, complete connector free. Then you can throw that in the water, no problem, right? It's convenient, it's safe, you have environment, and also very clean. Okay, so does not have carbon residue. Often for moving devices, it has carbon brushes, which generates a carbon residue, which is a problem for semiconductor manufacturers. And there are other situations like biomedical implants. Okay, it would be a pain, right? Cause a lot of problem if you have a wire coming from stomach or from the brain. So clearly, there's a need for wireless power transfer, and also for different types of wireless sensors, actuators, and the IoT networks. And also new possibilities. There's a new capability, like machine tools, right? It's constrained by move of wires. Okay, if no wire, it enables new design. It's a new capability. It also makes standardization easier. Okay, if your connectors, physical change is difficult, it's costly. Right, so this picture from World Economic Forum, which lists in 2014 lists the wireless power transfer as one of the top 10 emerging technologies. How to achieve wireless power transfer? Well, we don't have much time to talk about details, but simply speaking, we all know transformers, right? Power transformers. If we split power transformer, separate power transformer, primary secondary coils, power almost cannot go through. Then how can we do it? How can we split it? Still get power across. Increase the frequency and do tuning, like radio. We know our other side, if we have radio, RF beaming, it's mainly for information, for communication, but it has power associated. It has to rely on power to exist. Then, another way is to split capacitor. We all know capacitor, there's no direct connection in between. It's a dielectric material. It's something called displaced current that's imaginary. Physically does not exist. If you split it, we can get power across. There are other ways, like ultrasonic power transfer, right? With ultrasonic. It was called acoustic energy transfer, but I don't like the name because we want power across. We don't want noise. So I call it ultrasonic power transfer, UPT. And you can use laser, we can use infrared, I could do energy harvesting. So some people say there's no problem with the energy shortage. Often we have too much energy, tsunami, storm, too much. What we need is technology to handle it, right? To store it for our use. Okay, so energy harvesting technology, it's quite popular now. And then there's other techniques that people still considering, but not regarded as a science. Scalar wave. It's a scalar wave guys claim it's beyond electromagnetic wave. It's faster than the solar, the rain speed, which is not proven yet. So basically, this diagram shows how it works. Okay, we have a primary coil. We need to have a power converter to create high frequency current, generate high frequency magnetic field. Then we have some secondary as a TX, receive power, but often it's weak and fluctuates, not stable. So we need to condition it, tune it, like a radio system, right? We need to tune it to make it to increase the power transfer level and then to change that into a form that we can use. Okay. So in terms of magnetic field coupling, that's a key feature of inductive power transfer. That's the most mature technology we are working on. This can be 1D, 2D, 3D. That's basically, so 1D is just one directional, follow one wire or coupled with a one point-to-point. It can be 2D. This one shows the Part 4 project, which has been demoed in our general library. It's gone. It's a part of general library now. So for half year, it's basically, as long as you stay in that box, it's on that surface, it gets power all the time. Finally, the mechanical system broke down, but our power supply continue worked well. And it can be 3D. That's a box. Use box. As long as it's box, its power is guaranteed. So one application is biomedical. So for biomedical sensors, and put sensors in the rat. As long as the rat inside, it receives power and can send signal out for 24/7 monitoring. This is very useful for biomedical for medical research and new drug test. Okay, in terms of configuration, there are different types. It can be tight, can be semi-tight, and can be loose. Okay, I won't go through too much details. There's a different configuration depending on the application, and different tuning methods, right? Like radio. So secondary side, we call RX, receiver, that's a tuning. Like radio, as we can do fixed tuning, we can do dynamic tuning. Okay, and the CPT, on the other hand, that's based on electric field coupling. So basically, we split capacitor, separate the two plates of capacitor, and then the secondary part can move, right? So I won't go through details, but in terms of configuration, it can be 1D, 2D, can be for rotary. So we did a lot of work on this. Application. So there's a need for it. Where it can be used? Well, power supply is generic requirement, right? So I don't think in all the cases we need wireless power, but in many situations wireless power provides a new solution which makes the system much better. We found many practical applications in industrial, biomedical, consumer electronics, transportation, robotics, mining, renewable energy, etc. Okay, so one example is, for example, wireless kitchen. Just imagine we have a kitchen top, so you can put your electric, like blender, cutter, or whatever there, you get power. That would be very, very convenient. Okay, research contributed by our group. The wireless power concept is not new. Tesla tried it more than 100 years ago, right? So 150 years ago. But many people followed up and tried to make it work, but it couldn't work because there's no good material, no good device, right? So people try to use electronic tubes. That's a very big, bulky, and lossy. They developed a demo, but it couldn't work. The first commercialized project was done by our group, led by Professor John Boyce and Andrew Green, who went back to Germany. And it was licensed to Daifuku for material handling system and Wampler for people movers. This is the first practically commercialized system. There we followed on. We still have a very big group, including Grant, Kovic, Udaya, so you saw him today, Julipa, and quite a few other colleagues still continue working on this and in many, many different areas like EV charging, biomedical, at the center. So I just show you, in my case, I have been involved in a company called Power Biprocracy. It's basically, we went through a Spark computation. Now it's called the velocity computation. And so there we got the second prize, runner-up. They continued work on it, and finally, after 10 years, Apple acquired it. And the good thing is that company stays in Auckland, so they are recruiting a lot of our students, and also we work closely. That's one example. Another example is biomedical applications. We had an interdisciplinary group, including our department, bioengineering and medicine. Okay, so that's we have been doing that for quite many years, and you can see I was quite young that time. Yeah, so we got quite a few projects, government fund projects, and also biomedical sensor side, biomedical wireless power biomedical sensors are commercialized. Yeah, another is a heart pump. We got a prototype, but they couldn't commercialize because it's safety reasons. It's hard to pass safety requirements. So that's the initial work we did for biomedical system. That's that's the earliest reported work by our group in IEEE biomedical circuit systems. Another example, renewable energy. This is still working on this, not commercialized, but just imagine PV system, right? PV panels have many connections, right? Connectors. So all people in electrical engineering know connectors are weakest link. Often stats shows more than 90% of problems occurred at connections. Okay, if we get rid of that connection, the system will be much more reliable. Imagine you have PV panels, you can just put it there directly for installation. If one piece is faulty, you just replace it without any connection. Okay, there we just try to collect power underneath. We don't need to drill a hole on the roof. Many people are concerned about the roof PV because they're concerned it's not sealed well. That's what they call the water tightness problem. Okay, generally it's a wireless power still at its early stage. So we have been doing this for over about 30 years. So we have found many practical applications, but still it's only limited to short range. Yeah, that's the last one. Yeah, very limited to the last. It's basically both technologies are in near field. That's mainly what we are doing. At another group, in radio systems called MTT, microwave stereo technology. So they are working on long distance power transfer, but they haven't got any products because of safety, efficiency, EMC issues. So there are a lot to do, and to develop a real wireless power transfer system. Often I use standard name called wireless power transfer, but I often call it contactless because when I say wireless power transfer, the first question they ask, how far can you go? We couldn't go at this stage, we couldn't go very far, like the phone you use, right? So the phone system, charging system, is called MagSafe. Use magnets to hook there, okay, just to solve the connection problem. So we need more people to work together from university, design engineers, and the industry to work together to make practical systems which can really wireless power our society and make people's life easier and more convenient. Thank you.